I sort of interpreted what Spencer was going to talk about as the axisymmetric Hadley cell, and then I'd follow with the eddies. But Spencer has already talked a lot about eddies, but he's mostly been focusing on the effective eddies on the ascending and descending branch positions, so the width of the cell and the position of the cell. I'll talk much more about the strength. Before I get into that, I just wanted to show this figure because I remember when Spencer was talking about angular momentum and sort of, blowing on a spinning ball, I think people didn't quite believe him that you can change the rotation of the Earth with the atmosphere. But this is a plot I made, and in the red is the relative change in the angular momentum of the atmosphere, just taken from NCEP reanalysis. Very simple calculation. I just used the pressure level data and added it up. You could do it much better than I've done it, but it was a very simple way. And then the blue line, I looked on the internet, and there's a GPS data set that tells you the length of the day. The length of the day varies, so it's in milliseconds. So it's 1 millisecond difference per day, and it's very important for the GPS satellites. They need to know exactly where they are. And I just plotted them against each other. These data sets are completely independent as far as I can tell. The reanalysis is a model that runs and sort of takes in atmospheric observations, and the GPS satellite is a satellite that looks at the Earth. And it's pretty good. So when the angular momentum of the atmosphere is high, the Earth's rotation has to slow down a bit because you have to get that angular momentum from somewhere, and it comes from the Earth. There's an exchange of angular momentum between the Earth and the atmosphere, so that when the jets are particularly strong, the Earth is a bit slower. And so there's a very clear seasonal cycle here. I think it means that the length of the day is a bit longer in the southern hemisphere winter because the southern hemisphere jet is a bit stronger than the northern hemisphere jet, and it's strongest in winter. And there's a sort of interannual variability which is related to ENSO, as every other interannual variability is. And there are some trends. The trends I'm less sure about whether they're real because it's free analysis. And of course, there's a very, very long-term trend associated with the moon. So the moon is getting further away from the Earth, and that's slowing the Earth's rotation. I think that doesn't show up on this. I think that's just way, way too slow. But I thought that was kind of cool. No, I didn't make it just that. I made it a while ago for my class. But there is a paper in Nature in like 1970 something where they first make this point. Because when I found it, I was like, oh wow, this is actually pretty cool. But yeah, people know about this. Oh, it's there. So the trend is global warming. Wow, okay, crazy. Okay, so I'm going to talk about eddies and the Hadley cells. And first, I want to recap a little bit of the axisymmetric theory, which Spencer talked about a bit. So let's think about an angular momentum conserving Hadley cell, in particular, the Helden-Howe model, which is this model for the equinoctial case. And so you imagine this is the Earth's surface. So the model basically has three components. One is there's a rising branch at the equator. So if this is the equator and this is the pole, you have this rising branch. And that air rises at the equator and it takes the angular momentum of the Earth's surface and it homogenizes that vertically. So here in this first branch, m equals the angular momentum of the Earth. So the m is just the angular momentum here. And it takes the angular momentum from the equator where the air is rising. And that's kind of an assumption in this model that's symmetric in each hemisphere. You can relax that as well. And the second part is the air flows poleward in the upper troposphere, and it conserves its angular momentum, so the m is constant along this branch. And the third part of the model is that air returns near the surface, and there we assume that the Earth's friction is enough that the angular momentum is not too different from the Earth. So that just means that the zonal winds are weak. Right? If m equals the planetary angular momentum, the zonal winds are weak. And so this gives you this picture of the winds associated with this model. This is latitude, and this is the winds. And in the upper atmosphere, because you're conserving angular momentum, you're producing a really strong upper level jet. So this is let's say the tropopause. And near the surface, we assume the winds are weak. And so you get something like a wind field like this. And as Spencer pointed out, you need a sort of balance between easterlies and westerlies. And so if you go through the model, you can actually get an estimate for what that is, and you get easterlies in sort of the deep tropics and some westerlies for the poleward. Okay, so this is sort of a very basic sketch of the Helden-Howe model. Okay. And Helden-Howe actually did some numerical solutions of this model, and this is what it looks like. So it's actually 6 panels. It looks like. This is the zonal wind on the right, and this is the stream function on the left, and it goes from 0 degrees to 50 degrees and 0 degrees to the pole. And so you see, you've basically got westerly winds almost everywhere except in this region near the equator. So the shaded is easterly winds and a very strong jet at the edge of the Hadley cell. And there's 3 solutions here, and they differ in this viscosity that's added. So the Helden-Howe model is in what's called the nearly inviscid limit. So the analytical solution that they give is for the solution you get if you take the viscosity in the limit that it goes to 0. But you can't do that numerically. You have to have a viscosity. And so they looked at how this depends on viscosity. And so you see the top one is the strongest viscosity, bottom one weakest viscosity. So as you decrease the viscosity, maybe unsurprisingly, you get a stronger jet. So you get closer to this angular momentum conservation. But somewhat weirdly, the strength of the cell goes down. And it doesn't just go down a bit. It goes down by a factor of 4 or 5. It goes, sort of in this range, not so far off linear in the viscosity. So that's a bit weird because the model itself is nearly inviscid. It's supposed to not depend on viscosity. But even in the range of the viscosities that you can stably simulate, so this was, they were trying to go as low as they can, but it never really converged. It gets very sensitive to the viscosity. So what's going on here? Well, let's go back to our picture. So you've got air coming in near the surface, low winds, rising at the equator, conserves its angular momentum and this jet. But I have not drawn the descending branch. And so if you think about the wind profile I drew, sorry, I'll go back. At the edge of the Hadley cell, in the upper troposphere, you've got this huge jet. At the surface, you've got, by assumption, low vertical wind speeds. So you have to bring air down in that descending branch and somehow connect it to the boundary layer that has low surface winds. So you need to take out you need to get that upper level wind down to a very small value at the surface. So how do you do that? So we're thinking about how you do this. Now there's kind of 2 ways you can do it. One, where do I write this? Clean this up. Okay, so one way of doing this is to actually have a slanted descending branch. So if you take that air from the upper troposphere and you bring it down so that by the time you get to the boundary layer, you're near the equator again, then you can conserve angular momentum and you've lost that jet. So as you go back, you're going to follow this same path and end up with a small velocity. That's one way. And the other way is to remove angular momentum through some sort of process. So if you bring the air directly down, you've got to remove that angular momentum somehow. And so that's what's happening in the Helden-Howe solutions. So this is actually an example from some of my work where you can see these 2 different solutions. So this is simulations of a sort of quasi-axisymmetric Hadley cell. So I just had a very narrow, essentially a narrow beta plane that I was simulating the atmosphere on. And I developed a Hadley cell similar to the Helden-Howe Hadley cell. And what I'm plotting is in the red lines, angular momentum contours. So angular momentum changes as you cross these contours, and the stream function is in the solid lines. And so in this what I'm calling low viscosity case, you almost conserve angular momentum in this part. There's no contours of angular momentum in the Hadley cell. But to do that, you need to bring that down at a slant. And so by comparing the upper tropospheric latitude is maybe 20 degrees, at the surface it's closer to 10 degrees. And of course, numerically, you can never go to 0 viscosity. So if you really want to go to 0, you'd have to bring that all the way down to 0 degrees latitude. That's one way of doing it, but evidently that's not what's happening in either the Heldenhauer solution or in the atmosphere, because we don't have this descending branch. And so the other way is the top plot, which is where you have streamlines. Oh, thank you. The top plot, you have streamlines that cross angular momentum contours. So whenever that happens, you're not conserving angular momentum. So there's got to be some force or some torque that takes angular momentum out of the descending branch. And so if we think about these solutions, they indeed have fairly vertical descending branches. So something's taking angular momentum out. And the thing that is taking angular momentum out is this viscosity in this case. And so the higher the viscosity, the better you can take out angular momentum of the descending branch, and the stronger the cell can be. Because you can think of, there's a certain time scale that you would need for the viscosity to remove angular momentum in that descending branch. And that's how long the parcels will have to spend in this descending branch. And as you increase the viscosity, that time scale goes down. You can actually have more mass flux in the cell. So that weird result that the Heldenhauer model actually depends on viscosity, it suggests there's something missing in that model for the real world. And what it's missing is eddies. So in the real world, we don't have, the viscosity is sort of 6 orders of magnitude smaller than these numbers I'm showing you. But there's non-axis symmetric motion, which allows eddies to take angular momentum out of the subtropics. And so we're going to think about how that works. Okay, so you can write the equation for angular momentum in the atmosphere as the following. So the left-hand side here is the Lagrangian rate of change of angular momentum. And the right-hand side, F lambda is the, sorry, I don't know why, I'll call it lambda. F lambda is the friction in the zonal direction. So the notation I'm using here is lambda is longitude and phi is latitude. And m is the angular momentum, which I'm writing down now. So RE here is the radius of the Earth. And omega, which you can barely see because my writing's so bad, is the rotation rate. And so this bottom part has two components, the planetary angular momentum, so that's the angular momentum associated with the rotation of the Earth, and this U is the zonal wind, which is the angular momentum associated with the motion, so that's the relative angular momentum. So friction here is actually the small scale friction. And so that tends to be in the free troposphere, very small, and in the boundary layer, large enough that it's important. So let's think about this equation. So what is the Lagrangian derivative actually? Well, we can write it in the following way. So the Lagrangian derivative is the partial derivative with respect to time plus the advection. And I'm writing the advection here as a horizontal part, which is V times the horizontal gradient of M, and a vertical part. And I'm using pressure coordinates just because it makes things a bit easier. So omega is the vertical velocity in pressure coordinates, and dVp is the vertical derivative in pressure coordinates. And so we can convert this into flux form. And so if you haven't seen that, the idea is that I take these two derivatives here and I use the product rule on them. And so what you can get is dm dt, changed color, interesting. You can write them instead as this divergence. And then you need to subtract the other part of the product rule. So then you get m grad h dot b minus m del omega del p. But this part here is zero by the continuity equations. The continuity equation tells you that grad h dot v plus del omega del p equals 0. And so this is a very common thing that we do in fluid dynamics, is converting from advective form to flux form. So if you haven't seen that, it's something that sort of happens all the time. And so when you get to my age, you just see it and sort of what happened. But but when you first do it, it sort of is a tricky thing. But this is equivalent to the advective form that involves just the Lagrangian derivative. Okay, so we have then this equation, mdt plus grad h v times m plus dp omega m is equal to this frictional torque. And I should say this angular momentum equation, it basically comes from the primitive equations, derived from the primitive equations that angular momentum is conserved except for this frictional force. Okay. Okay, so now I'm going to break things into a mean component, a zonal and time mean, and an eddy component. And so if we take the zonal and time mean, and remember that you can write products like this, Bm in the time and zonal mean, as a mean part plus an eddy part. So, and if you haven't seen that before, you basically you can break everything into a mean plus an eddy component. That's just a sort of mathematical thing. And then when you multiply two parts together, you get 4 terms because you multiply out 2 by 2. But 2 of those terms are 0 because they're just the mean of a perturbation. And so you end up with just these 2 terms, which is the mean flux, so the flux by the zonal and time mean motion, and the eddy flux, which is the flux by the deviations from that. And so those are the eddies that we're going to think about. In an axisymmetric fluid, we don't have this term. This term is purely present because of eddies. Okay, so we'll do that decomposition, and we also assume that we're in steady state, and so we can neglect this time tendency term. So then on the left-hand side, we have grad h Vm, and I'm just going to take the mean part. And then I'm going to take the other part to the right-hand side. So then I have minus grad h v primed m primed minus del p omega prime m prime. So I've basically just taken the eddies to the right-hand side, because we can think of that as a forcing onto the mean part, which is what we're interested in this case, because we're thinking about the Hadley cell. Okay. And you can do one final thing, and that is that because we're in flux form now, but I can actually just switch back to advective form for the mean component, and you apply the mean mass conservation equation. So you can put this back into V dot grad h m plus omega ddp m, and that's all averaged, equals re cos phi times, and sorry, this should be the mean of the frictional force. Okay, so what are these V primed, M primed terms? What are these fluxes? Well, M, sorry for scrolling, but M is this quantity up here. And it has a bunch of, it has a planetary component and a relative component. And the planetary component can't change in time or zonally. Right? It just depends on the planetary rotation. Basically, it depends on F. So when we take M primed, the only thing that we need is the U part. So the perturbations to M are just the perturbations in the velocity. So we can apply that here, and we get V dot grad h m Yep. Yes, zonal and time mean. Yeah. Deviations from that mean, yeah. You can do this as a zonal and a time mean separately, and then you end up with the transient eddies and the the stationary eddies. I just haven't bothered with that. So all the eddies are in one. Okay, so then you get this equation where you have the advection of angular momentum on the left-hand side, and the right-hand side is the forcing terms on that mean angular momentum, which is friction, and these two angular convergences of momentum. So U prime V prime is the flux of momentum zone, meridionally, and omega prime U prime is the flux of zonal momentum vertically. Okay, and I can simplify this a bit further. If we take a zonal mean, we don't have to worry about zonal advection, right? We've taken a mean, and so all means of zonal gradients go away. And so this just ends up being the meridional component plus omega dm bar dp. So that's the left-hand side equals re cos phi. I'll just write this up and then I'll explain it. Okay. So we've got the advection on the left-hand side. So I'm in spherical coordinates. So this is the gradient in latitude, and then you have to include the Earth's radius to get that as a distance. So it's basically just the meridional gradient multiplied by V, as you would normally have for advection, the vertical advection. And then we have this divergence in meridional direction and the vertical direction. I've included that from above, and friction as we had above. And so I'm going to call this term that involves the eddies, the eddy momentum flux convergence, and I'm going to call that minus S. So S is the eddy momentum flux divergence. Okay, and so now what I want to do is apply this equation, but I apply it in a particular place, and you'll see why I do that in a moment. So if we imagine the stream function of the Hadley cell to be looking like this, so this is sort of latitude, height, or pressure in this case. And so you have some overturning. And so what I want to do is think about this location from the stream function maximum up to the tropopause. So I'm just going to take one sort of band of the atmosphere and apply this equation there. So the reason to do that is that at the stream function maximum, the motion, the zonal mean motion is quasi-horizontal, right? Because you don't have the rising motion from the ascending branch or the descending motion from the descending branch. You just have horizontal motion. So we can ignore this vertical advection. What else do we have there? We're in the troposphere above the stream function maximum. We assume we're not in the boundary layer anymore. So we don't have a sort of tropospheric depth boundary layer, so we can neglect friction there. And so then we get this much simpler equation, although it maybe doesn't look so simple to you yet, but it will become even simpler, where we take the advection of angular momentum, zonal advection, and that just equals this eddy momentum flux convergence, so the negative of the divergence, times a moment arm, essentially. So Re cos phi is just the distance to the axis. So we're relating V, so this is something to do with the overturning circulation, to the eddy stresses, to the effect of eddies on the atmosphere. Let's go a bit further, and let's expand this derivative on the left-hand side. So just putting in the definition of M, we have U bar Re cos phi, so that's the relative angular momentum, plus omega Re squared cos squared phi, that's the planetary part, and that again equals minus S Re cos phi. And so I'll spare you a little bit of the maths, but you can go through this, and what you get is an equation like this. that's the relative part, and you end up getting something very familiar for the meridional gradient of the angular momentum. So because we're in spherical coordinates, it might not be so obvious, but this, it turns out, is the negative of the relative vorticity, the zonal mean relative vorticity, and this is the planetary vorticity. So this is just F. And that seems kind of unbelievable at first, but it is true that the gradient of the angular momentum is the vorticity. And yeah, I encourage you, as Spencer did, to do this derivation when you have a chance. Okay, so we can write this in a really simple way then. We get V times F plus theta. Oh, I've got a sign problem here, but that's okay. So this was minus the negative, minus the relative vorticity is minus the relative vorticity and minus F. So I get F plus zeta here, where zeta is the vorticity, and I've taken a bar because it's the zonal mean, and then I've changed the sign on the right-hand side. So now we've got a really simple equation that tells you something about V, something about the poleward flow in the upper troposphere. So this is now we're getting very close to something associated with the Hadley cell. And it depends just on the eddy momentum flux convergence. It's supposed to be the divergence. Okay, so we can do one more thing with this, and that is we can integrate it in the vertical. So we know this equation applies in this region above stream function maximum in the Hadley cell where the flow is quasi-horizontal. And so we can take an integral from this location up to the tropopause. So let's do that. Okay, so what I'm going to do is I'm going to define first a Rossby number. So this is FV is 1 minus the Rossby number. So the Rossby number here is the ratio of the relative vorticity to the absolute vorticity. And that should be a mean. So if you think about the mid-latitudes where you have quasi-geostrophy, basically the condition for that is that the planetary vorticity dominates the atmosphere. So the relative vorticity is always much smaller than the planetary vorticity. So that's why this is a Rossby number, because if the Rossby number is small, you're in this quasi-geostrophic regime. You're in the regime where you can apply geostrophic balance. Okay, and then I integrate it vertically. So and I'm going to do one thing, and that is to assume that the Rossby number is constant in this integral. Now, that's not true, and you could sort of define a sort of a weighted mean Rossby number that allows the equations to still work, but it's just simpler to assume it's constant. So then I get 1 minus rho times this integral of V dp from the tropopause down to the PM, which is the level of the stream function maximum, and then that equals S on F. And then that S is also integrated over the same region. So I'm going to just define these arrows as being an integral. So the integral from PT to PM of whatever it was, dp on G. This is should be G. So that dp on G just gives you a mass-weighted integral in the vertical. Okay, so now what is this thing? This is V summed in mass over that whole region from the stream function maximum up to the tropopause. So we're integrating all of this mass flux through here. So that's very closely related to the stream function maximum. So this thing is actually just, where is it? We know that psi, the maximum stream function, is 2 pi re cos phi. So it's just the length of a latitude circle times this integral. So that means we can write this equation in terms of the maximum stream function. And this is where I wanted to get to. So we have on the left-hand side the maximum stream function of the Hadley cell. So this is one of the most common measures of the strength of the Hadley cell, how much mass over turning you have. And on the right-hand side, we have the eddy momentum flux divergence or the convergence. Can you help me out, Spencer? It's got to be the divergence, right? Yeah. So that is the eddy momentum flux divergence. There might be a sign error in something I've done previously. No, it's all right. Okay, great. And the thing that connects them is this thing called the Rossby number. This is the thing that Spencer talked about. It's how close we are to that angular momentum conserving limit. It's also how big the relative vorticity is compared to F. And it's how close we are to this quasi-geostrophic limit as well. So let's think about what those limits are. Is that integral? Great. Okay. So there's two limits that are easy to think about. One is what's called the linear regime. So this is where F is much greater than the relative vorticity. So the Rossby number is very low. It's close to 0. And so that equation then tells us that 1 minus the Rossby number is close to 1. And so the stream function maximum, psi max, is exactly proportional with some constants to the eddy momentum flux divergence. So in that limit, the strength of the Hadley cell is how much momentum you can suck out of the subtropics through eddies. So maybe, yeah, here. So that's this bottom limit, right? In this, the top limit. You can see in the descending branch, you've got angular momentum contours crossing stream function lines. So there is where you have to change the angular momentum, and so you're pulling angular momentum out of the subtropics. And the second limit is the Held-and-Howe limit. So if the Rossby number is 1, then the equation that I wrote down, I actually might write it down so that it's clear. Psi max times 1 minus the Rossby number. Let's just make sure I get it right. Equals this eddy momentum flux divergence. So if the Rossby number is 1, then the left-hand side is 0. And if the Rossby number is 1, we must have that we're in the angular momentum conserving regime, so we can't have any eddy stresses. So S must also be 0. So the equation just tells you 0 equals 0. So in that case, the Hadley cell does not depend on the eddy fluxes, and we can think more in terms of the Held-and-Howe model. And as Spencer said, the Held-and-Howe model tells you the strength of the cell by thinking about the thermodynamics. This is quite a sort of profound result, actually, when you think about it. In one regime, you only need the momentum budget to think about the strength of the Hadley cell. We only need to know how much momentum has been taken out of the subtropics through eddies. Now, maybe those eddies depend on the thermodynamic budget, fair enough, but directly, we have this connection between eddy momentum fluxes and the strength of the Hadley cell. That's completely different to the nonlinear regime, where now the momentum budget doesn't tell you anything about the strength. It just gives you 0 equals 0. And so now you've got to appeal directly to the thermodynamic budget. So the Hadley cell can respond. If you force the Hadley cell differently, you change the equilibrium temperature, for instance, the RCE temperature, and you strengthen the temperature gradient, then you'll automatically expect that you'll strengthen the Hadley cell. That can't happen directly in the first regime. It only can happen through changes in the eddies. And so you've got to think about eddies. Okay, so the big question is, what limit is most relevant? And so this is a paper that Spencer mentioned, Walker and Schneider in 2006. And what they did was run an idealized GCM over a very wide range of parameters. These parameters included the rotation rate, so they changed the rotation rate. I think they changed the radius of the planet, which sort of does the same thing. They changed the height of the tropopause. They changed everything they could. And it was a very idealized situation. It was all equinox. And then they plotted these two things. So this is the eddy momentum flux divergence I was talking about, and the Hadley cell strength, the strength of the circulation. and the one-to-one line is the dashed line. So if the Rossby number is exactly equal to 0, you expect the solution to lie on the dashed line. And what they found was that was, pretty true over a large range of parameters. So these are log-log plots, so that means both that there's a huge range of stuff going on here, but also that small deviations are actually maybe not so trivial from that line. But nonetheless, what they showed was that for this idealized model at least, the small Rossby number limit was much, much more relevant. And this extended to things like if you looked at the scaling that you get from the Helden-Howe model for how the Hadley cell should change, it gave you the completely wrong answer. And they developed some scalings based on thinking about these eddies instead. That's an idealized model, but what about the actual atmosphere? So this is a plot from reanalysis, and the red lines again are angular momentum contours. The overturning is shown in the solid lines, and the Rossby number is shown in the colors. And so white is sort of below 0.2, and then you get colors going up. And so you see, for the equinox, so this is the annual mean, the angular momentum contours are regularly crossed by the descending branch of the cell. So we definitely have some angular momentum transport going on. And secondly, the Rossby number is pretty small. So in most of the sort of, if you think where we integrated in that equation, that's sort of here. And for most of that, the Rossby number is pretty low. So if you were to define a mean over that, it'd be something like 0.2 or 0.3. And so that tells you that, there's not much room for the Hadley cell to respond except directly to the eddies. Okay, so how does this then work? What are these eddies that are doing this eddy momentum transport? Now, it turns out that the dominant eddies that exist in the subtropics are Rossby waves that come from the mid-latitudes and break in the subtropics. And so this is where this Rossby wave chromatography idea that Spencer mentioned comes in. So we can think about sorry, this is a very southern hemisphere way of doing this, but latitude goes downwards on this diagram. So think about the zonal wind in the upper troposphere. You have a jet in the atmosphere, which might look like this. And then where the jet is strong is where you have strong temperature gradients. So this is, sort of mid-latitude region. And this is where you're going to get a whole lot of energy, eddy generation. Eddies are going to be generated here. And those eddies will have a range of phase speeds. And so we can also plot on this diagram the phase speed. And so the yellow might be a distribution of eddies that you produce, distribution of Rossby waves that have phase speeds in that regime. And the one thing we know about Rossby waves is they have to propagate west relative to the mean wind. So they have to be to the left of that red line in their phase speeds. And then they're going to propagate north and south. And one thing that is true about these waves is that when they do that, they tend to maintain their phase speed. So they propagate north and south, but they maintain their phase speed. But we still have this problem that they can only propagate if they're to the left of the red line. So once they hit this red line, they have to stop propagating. And they do that by breaking. And so that's where you get breaking waves in the subtropics. And so those waves break in the subtropics, and it's sort of a property of Rossby waves that they actually propagate momentum away from, towards their source. So when a Rossby wave propagates, it's pulling momentum from where it breaks to where it was formed. And so that's how the Earth's atmosphere deals with this fact that the Hadley cell needs to have angular momentum come out of it for the descending branch. On Earth, that comes from eddies in the mid-latitudes propagating into the subtropics and breaking there. And so that gives you this really close connection between mid-latitude Rossby waves and the Hadley cell. So not only is it are they really important for the edge of the Hadley cell? They're really important for its strength. Okay, how am I going for time, actually? Okay, are there any questions right now? Yeah.
A bit about like mechanically how that happens. Like, so you have Rossby wave propagation and they break. So does the energy kind of come out of the Hadley cell, or do they impart energy to the Hadley motion? Does that make sense?
The energy, I have to think about the energy, but from the momentum point of view, yeah, the mechanistically how it works is that, you know, you think of imagine you've got sort of a low pressure system like this, it's symmetric. And you want to know the fluxes of momentum. And the flux of momentum is U times V, averaged over that eddy. And so if you think about, you know, in this quadrant, U and V are positive. So if this is a clockwise circulation, but in this quadrant, U is positive, but V is negative. So those two different parts of the eddy have different opposite momentum fluxes. And that's true of the south side of that too. But if you have a tilted trough, and now on the left side of that eddy, U and V are both negative. Sorry, what am I trying to say? U is negative, V is positive. So this thing is negative. And on the right side, U is positive, but V is negative. So UV is also smaller than 0. So if you tilt the eddy, then you can actually produce a momentum flux. And so if you tilt it backwards, then you produce a southward momentum flux. If you tilt it forwards, you produce a northward momentum flux. And I have a picture, which I'll try and find. Okay, so that's what I was just saying before. If you have these different tilts, then forward tilt gives you a net northward momentum flux, a backwards tilt gives you a net southward momentum flux. And so when you look at these eddies, when you look at the tilts of these troughs, you tend to find in the subtropics, there's a backwards momentum flux, that's a southward momentum flux. And so that's just sort of how the Rossby waves behave, is that they flux momentum from in the opposite direction to where their energy is moving. And so you tend to have a convergence of momentum towards the source of Rossby waves. And that's what causes the jet, but it also takes momentum out of the subtropics and can spin up the Hadley cell. Yeah.
So is that the reason the negatively tilted troughs sort of intensify and the positively tilted troughs do not?
That's a different tilt. So that's a vertical tilt, actually. Whereas this is a horizontal tilt. So yeah, in baroclinic instability, you need a vertical tilt, backwards tilt of the troughs to produce that energy. But this is all a completely barotropic argument. So that means it's an argument that doesn't depend on the depth.
I think that negative tilt refers to the, I think the horizontal circulation. It's a general thing that
but the tilt in the vertical. It's the horizontal circulation tilting.
Yeah, there's a tilt in the vertical, but people usually in the operational forecast check for the tilt negative on the horizontal, like tilt towards the, you mean the negative side. If you consider horizontal kind of a surface, that tilt in the negative side is favorable for frontogenesis or intensification, whereas the tilt towards the other side, positive side, is not that favorable. They say frontolysis. So I was trying to connect whether this tilt is sort of connected to that.
Yeah, usually from that point of view, I usually think of it as whether the trough is further westward as you go up in the atmosphere. So that kind of tilt in the vertical. I don't know about how the horizontal tilt relates to fronts. That's usually more of a kind of kinematic thing about whether there's diffluence or confluence. But it might be related, I'm not sure. Any other questions? Okay, so I'll just quickly do one last thing, which is, so this was all for equinox. But the question is what happens with the seasons? And let me now go back to my original presentation. This one, okay. So this is now, the top plot is for the annual mean and the bottom plot is for July. And what you see is in the July case, if we look at, oops. Now it's a bit tricky here because doing this calculation right near the equator doesn't work so well. But if we look sort of just near where the stream function maximum is and look upwards, we see we get quite high Rossby numbers in the upper troposphere. And Spencer's plot also showed that during the solstitial seasons is when you get the highest Rossby number. The solstitial season is when the effect of eddies is weakest on the Hadley cell. And the reason for that is at least partially because of the wind distribution itself. So the black lines separate easterlies and westerlies, mean easterlies and westerlies in the atmosphere. So this region out here in the top plot is westerlies, and these are westerlies here. And there's easterlies in the middle. And we know that Rossby waves need westerlies to propagate. So any region of easterlies will kind of shield you from the effect of mid-latitude eddies. So in the in the equinoctial circulation in the top, you have westerlies above the stream function maximum. So those are through most of the cell, you can get eddies propagating in Rossby waves from the exotropics and breaking. And so they can efficiently affect the Hadley cell. In the solstitial case, for a large portion of the cell, you're in mean easterlies. So this kind of shields you from the effect of eddies. And so this idea, where do I have it? Maybe I have to draw it. Yeah, okay. So this gives you the following kind of picture. So this is the surface. And then I'm going to plot the wind. So for the equinoctial case, we have the equator in the middle here. And we have a temperature profile that maximizes. So that might be the temperature. Now, if you think about thermal wind, as Spencer showed us, if you have a poleward decreasing temperature, you get westerly winds in the upper troposphere. So this tells you the upper troposphere will look something like this. You'll have westerlies everywhere. So the eddies can come along and they can propagate almost to the equator, depending on the exact distribution. Actually, in reality, you do get some easterlies near the equator. So that's the equinoctial case. Now, what happens in the solstice is that the maximum of the temperature is now off the equator. It might be somewhere over here. So now, if we separate the atmosphere, in this region here, we have temperature decreasing towards the pole. T decreases toward pole. And that's true over here too. So here, T also decreases towards the pole. But there's this part between the equator and the maximum in temperature where the temperature increases towards the pole. So this is the place where the upper troposphere you expect to get easterlies. And so your wind distribution is going to look something like this. You've got easterlies here and westerlies over here. And so the temperature distribution associated with the thermal maximum moving off the equator itself produces a wind distribution that can protect the atmosphere from the eddies. So this is the mechanism that Simona Bordoni and Tapio Schneider kind of elucidated that gives rise to a kind of regime transition in the Hadley cell. The equinoctial case is far away from this angular momentum conserving limit, so it's controlled by eddies. And then at some point, the atmosphere switches, and this can happen very rapidly. And this is sort of one explanation for why you might have a rapid monsoon onset, particularly in South Asia. And then you're in this other regime, and this is especially true over South Asia. You have this big subtropical high in the upper troposphere that's associated with a very strong negative vorticity. And remember, the Rossby number is F plus zeta. And so if zeta is very strongly negative, then F plus zeta is close to 0. So that's close to Rossby number of 1. And so you end up with a high Rossby number, and you're in a different regime. And so this is sort of one theory for the monsoon, in a sense. The monsoon is this transition of at least a local Hadley cell into this angular momentum conserving regime. And so I think I better stop there.
Hello, thank you so much for the talk. I have a naive question. I didn't understand how in the non-linear regime of the balance between vorticity and eddies, how does the eddy term goes to 0?
So in order to have a Rossby number of 1, you have to have 0 eddies. There's no other way. So it's not a, it's still a diagnostic thing, right? The eddies are changing the vorticity. And so if you have eddies, they'll change it in such a way that the Rossby number will be smaller than 1, such that that momentum balance is satisfied. But like any budget, it's very, you can't, from the budget itself, tell what the causality is.
Thank you.
So that's why the theory for the Rossby number is the holy grail of this kind of work, I guess.
Thanks.
Which Spencer's going to tell us next year, right?
Other questions? So Marty, actually in your plot, you show Rossby number in the upper troposphere goes to 1 just to the south of the equator.
Yeah.
Is it, I mean, how is the background wind there? Is it westerlies or easterlies?
It's definitely easterlies in this plot.
Where the blue is darkest
Yeah,
is still easterlies.
Yeah, just because so the boundary is that black line. So the mean easterlies start here.
The
easterlies
black
start
thing
there,
is.
Yeah.
But what happens in the north? Yeah, what happens in the right? I mean, as the rising branch happens and starts approaching equator, and we see tropical easterly jet typically. Do we know why high Rossby number? I mean, Rossby number equal to 1 regime is not seen there.
On this side?
Yeah.
No, I don't. So it's tricky because in this region, I just haven't plotted anything because it's the Rossby number is basically dividing by F, so it goes a bit crazy. But then, yeah, on the northern side, the Rossby number is very low, actually, in this plot. Do you know why that is? Yeah, I mean, you can kind of, if you sort of take my equation as the only thing you care about, you only care about the Rossby number in that strip that you integrate above the stream function maximum. But of course, it does matter in other places, and so it's a good point. I don't know, actually. I can't remember. I've blanked on what. Did I define a generalized Rossby number?
Yes. Rossby number tells you if when the flow is horizontal.
Yes. Yeah.
If you're constant.
That's right.
But when you can still be angular momentum
Maybe I think this is probably worth.
Yeah, no, I'm remembering now, right?
Yes.
So the Rossby number is defined based on V times the gradient of angular momentum. And that was assuming that there's only horizontal motion. But in this region where there's where the ascending branch is, it's obviously very strong vertical motion. So you can include the vertical component. And then I think there you might actually get a very different answer because it's such vertical flow. And that was, I did that. I really forgot about that.
Can somebody pass her the mic from the last? Yeah. I think, yeah, the closest one is there.
It was because you reviewed the paper and made me do that.
Thank you for the talk, sir. So you showed a plot where you plotted latitude versus U, and it was a yellow region where that is
Latitude versus U. This
a
was
bell
by
plot.
hand or
Yeah, by hand.
like these plots?
Uh,
Or, oh, right, hang on. This,
yeah,
yes.
this way. Could you explain the dynamics again? How does it, if it reaches to the red part and it leads to the breaking, could you explain that part again?
Yeah, so this is sort of a, is another piece of dynamics, which is it's all sort of mid-latitude dynamics. But the idea is that it's called the phase speed spectrum, and the relevant paper is Randall and Held from 1991, I think. And you plot the zonal mean wind, so that's the red line, and then you plot the distribution of eddies as a function of phase speed. So you can Fourier transform the eddies and divide them into different wave numbers and different frequencies. And then the frequency divided by the wave number is the phase speed. So you can actually just plot them as a function of phase speed. And that just tells you, which eddies have what phase speed. And that's what I'm trying to represent with this yellow. So it's just, what are the eddies that exist? What are the Rossby waves that are propagating? And the one thing we know is that they have to be to the left of that red line, because they have to have a negative Doppler shifted phase speed. They have to propagate to the west to the mean flow. And so and then you observe that they tend to form, in this region. And then when they propagate north and south, so then they would move up and down on this diagram, and they tend to conserve their phase speed. So a Rossby wave won't change its phase speed as it propagates. And then that means it gets into a region where it's called a critical line, where it can no longer propagate. And from linear theory, you don't know really what happens there, but you know that it has to be absorbed. But non-linearly, what happens is the wave breaks. And so you tend to have wave breaking along critical lines. And so that's how we think about how the mid-latitude jet is actually maintained, that you get Rossby waves that form within it, and they propagate away and break away, and that produces a momentum flux towards the jet. And so that maintains the jet, but it also, because it's breaking in the subtropics, that controls, depending on the Rossby number, the Hadley cell.
Yeah, Marty, great talk. You mentioned that the switching between these two regimes is abrupt. I think Schneider and Bodoni also mentioned that. Do we know what part of the switching is abrupt? Is the temperature gradient itself changes abruptly, or is it the easterly that immediately emerges out of this balance? What causes this abruptness? Do you have an answer to that?
So it's sort of a feedback between once you stop eddies affecting the Hadley cell, you go into a different regime, and then that regime has a nonlinear strengthening of the Hadley cell with latitude as you push the thermal maximum further away. So once you're in that regime, the Hadley cells becomes stronger and stronger non-linearly as the thermal maximum gets further from the equator. And so it's sort of so the feedback actually is I think just present in the axisymmetric dynamics. And then what the eddies add is that they sort of are like a gatekeeper to it. So you can only have that once you've set up this easterly situation.
So if we can think of a causal mechanism, you need to have these temperature gradients set up first, which shut down these eddies, and then the positive feedback takes over.
Yeah, I think so.
Yeah, thank you.
Yeah. Let's thank Marty once again for a very nice tab plus PPT talk, which I quite like as a combination.